In this video, I'm going to talk a little bit about static and kinetic friction. And in particular, I hope that this discussion will help you better understand these two topics conceptually, but then also prepare you a little bit better for solving problems where static or kinetic friction might be acting on an object. So first, let's go ahead and talk about kinetic friction. We know that the word kinetic has something to do with motion. And so let's set an object into motion. Suppose we have a can of Coke that's at rest on a countertop. And we know that due to that can's interaction with Earth's gravitational field, there is a downward force of gravity that's equal to mg. And because it is at rest, it's being supported, its weight is being supported by that countertop, there's an upwards normal force that is equal in magnitude and opposite in direction. And in order to get this can moving, let's say I give it a push to the right, I am going to apply a force F to the right. And when I apply that force F and then let go, the moment I let go, let's say that this can of Coke is here, and now it has some initial velocity v0 to the right. And the moment I let go, only that normal force and that gravitational force would be acting on the can. But if there is some roughness between the surface there, between the countertop and the can of Coke, then there's also going to be a force that starts to cause it to slow down. And we know from our experience and from our intuition that when the can of Coke gets down here, in fact, the velocity might be zero, right? The thing would come to rest. And so in order for that thing to come to rest, not only can we have the normal force acting up and the gravitational force acting down, but there must have been some other force, some additional force, a frictional force, that points to the left. And so I'm going to label this frictional force a lowercase letter f, and I'm going to say that this frictional force must be present because I observe the thing going from some initial speed to a final speed of 0. So some force must be acting to the left in order to cause an acceleration that is opposite the direction of the velocity, which would cause the object to slow down. You might wonder about the origins of this force. Where does it come from? That doesn't seem like there is anything pushing or pulling on the object. If we were to zoom in on the space here between the can and the countertop, this location right here, if we could just zoom in, what we would see might look something like this. The bottom of the Coke can, while it is smooth, and the top of the countertop, while it is smooth, are not perfectly smooth, and so the surfaces can be rough. And so maybe the bottom of the Coke can looks something like this, and maybe the top of the countertop looks something like this. And so when those two surfaces interact, when you try to rub one of those surfaces past the other, they're not perfectly smooth. And so some of the countertop ridges get stuck with some of the ridges in the imperfections of the Coke can, and when you slide them past one another, they exert forces that oppose the motion that you're trying to cause. You can imagine if I try to push the Coke can to the left, it might get caught up in the ridges, and if I try to push the Coke can in the other direction, it might also get caught up in the ridges. And so if you just think about surfaces as being imperfect, as having some jagged edges, perhaps, then you can start to gain an appreciation for why the frictional force exists. And in particular, I think it supports a claim that you need to understand about friction, and that is friction always opposes the motion of an object. So if I throw the Coke can to the right, then the frictional force will always point to the left. But if I start on the right and move the Coke can to the left, the frictional force would point in the opposite direction. So one thing we'll need to remember about friction is that it always opposes the direction of motion. And that is, it requires motion, right, in order for us to make that claim. And so for this first example, I was talking about the friction that was acting on an object while it was moving, and for that we denote the phrase kinetic friction. Okay. And so the second example here, I have a box sitting on that same countertop. And let's suppose that the box is really heavy. And so the box has maybe a larger weight that points down and an equally larger normal force acting up. and I apply some force F. But when I apply that force F, the object doesn't move. And so despite the fact that the object hasn't started moving, there's still something opposing the force that I'm applying. So I applied a force to the right, but the object isn't moving, which must mean there's some force canceling that force that I'm applying. And so there must be some different kind of friction, not a friction that opposes necessarily the motion of the object, but that's opposing the force that I'm applying, that's preventing motion in this object. And for this, we denote the phrase static friction. And of course, we know while kinetic has something to do with motion, static means unchanging or the same. So right away I learned two important things about friction. If an object is moving and it's slowing down under the influence of friction, that frictional force is always opposing the direction of motion, always opposing the motion of the object. And if an object isn't moving, but a force is being applied in order to try and make it move, there must be some force preventing the motion of that object. And in many cases, it is a static frictional force. And I think if we think about the cutout that I made that zoom in between what's happening between the object and the surface, and the fact that those surfaces maybe are imperfect and have some ridges or jagged parts that can cause an object to get caught up or feel a force in the opposite direction that you're trying to make it move. The next thing that I'd like to talk about is, suppose I have a block and that block has a hook attached to it. And attached to that hook I have a string. And what I'm going to do is I'm going to take a force sensor or a force probe, a device that can measure the force being exerted on it, and I'm going to pull slowly on that hook, which is going to pull on that block of wood. And what I'd really like to do is I'd like to make a graph. And the graph that I'm going to make, let me get rid of some of this line. The graph that I'm going to make is going to be of the frictional force as a function of the applied force. And I'll talk a little bit more about what I mean by that in just a second. So the frictional force would be the frictional force that is acting between this block of wood and the counter. So suppose this block of wood is just at rest on a countertop, and when I start to pull on it, there's going to be a frictional force that opposes that pull. So there's that frictional force. And then all the time there's going to be a pull to the left from the force probe, from the string, from the pulling on that hook. And that force is going to be to the left, an applied force, capital letter F. And so I'd like to make a graph of the frictional force as a function of the applied force and see what we can learn about static and kinetic friction from that graph. Let's first talk about what would happen when I start to pull on that and the force that I'm pulling with isn't very big yet. What would happen is I would apply some force, and the force of friction would be exactly equal. And suppose I supply a slightly bigger force, the force of friction would be exactly equal. And the reason why I know that's going to happen is if an object has not started moving yet, so the forces I'm applying are so small that the object hasn't started moving yet, then the object is in equilibrium. And if the object is in equilibrium, I know the forces in that direction must add up to 0. And if the applied force and the frictional force are the only forces acting in the x direction, those two forces need to be equal and opposite. So until that object moves, those two forces are equal. And so there's going to be a range of my graph that's completely linear and going up. So no matter what force I apply on the x-axis, there's an equal force being applied, a force of friction, between the two surfaces. This will happen up until the moment where the object begins to slide, where the object begins to move. And the place on that graph where that occurs is going to be the peak of this graph. And so at this green dot, we often will say that the object is about to slide. It hasn't started moving yet, but it's about to move. If I apply any more force, then the object would start to move. Okay. So it's up until that point that the object is at rest. And what you would observe is if you continue to pull with any greater force, the object will start to slide and the graph will look like this. It will drop down and then remain at a constant value no matter how hard you pull on that force probe. And in this graph, generally speaking, we speak of two different regions of the graph. There's a static region on the left. This was the place where whatever force I was applying was not causing the object to move, and instead the force of friction that was acting on the block was equal to that applied force. But then on the right side of the graph, this region of the graph we call the kinetic region. And of course, the kinetic region is on the right because that's the place where the force that you were applying was large enough to not only cause the motion of the object, but continue to have it move. And so, in the graph, I observed two different kinds of friction, static and kinetic friction. And the reason why these two things are different will be important for problem-solving purposes, because we know that if an object isn't moving and a force is trying to cause it to move, then the force of friction that must be acting on that object is static. But if the object is moving and maybe is perhaps slowing down, or maybe it's just experiencing a force of friction as it moves, then we know that that's kinetic friction. And that's important for problem solving because the way we determine the value, or the numerical value of the friction, is different in each case. So let's talk a little bit about how I can get a number for the amount of friction, that frictional force. For the first part of the graph, I know that the frictional force is equal to the applied force. If you have a force probe handy, you can always measure that applied force because the force of the pulling would be equal to the force read by the force probe. But in that static region then, the force of friction is quite simply just going to be equal to the applied force. But that will not be true in the kinetic region. In the kinetic region, the force of friction is the same no matter what force I apply. And you could determine in a more careful experiment that that force of friction would be equal to mu, which we'll talk about in just a second, times n. The force of friction is equal to mu, which we call a coefficient of friction, times n. And in particular, we specify the type of mu, the type of coefficient of friction, as being the coefficient of kinetic friction. And so sometimes you'll see that Greek letter mu written with a subscript k for kinetic. And so this equation could allow me to determine the amount of kinetic friction, that frictional force, acting on the object. And we write a similar equation for the point where the object is about to slide but has not yet started to move. And there we write Fs for static friction instead of kinetic friction is equal to mu s, the coefficient of static friction, times the normal force. So I think when you are asked to calculate an amount of friction acting on an object, there's really three cases. If the object is about to slide, then you could use the coefficient of static friction times the normal force. If the object is sliding, it is moving, then you could use the coefficient of kinetic friction times the normal force. And if the object is neither moving nor about to slide, you would know that the force of friction is always equal to the applied force. So now I've introduced you to some of these equations, and I think I need to do some convincing. I need to explain to you why the frictional force depends on the normal force and why it has that other variable in there, these coefficients of static and kinetic friction. So first, let's talk about the normal force. Why would a force of friction be proportional to n, the normal force? Let's think about what the normal force represents. The normal force is how much the surface has to push up on the object. And let's suppose that the normal force changed. And how could I change the normal force? Well, I could push more down on the object, or I could lift it up a little bit. And you might be able to imagine, if you look back up to the picture that I drew in the top right corner, that if I was pushing down on that Coke can, then where the Coke can meets the surface, those two objects would be in contact, but I'd be pushing down on that compressing those objects into one another, and maybe that would make it harder for one object to slide past another. And similarly, if I had zoomed in on the package, the second example that I had, the box that I couldn't get moving, if I were able to pull up on that object a little bit, maybe it would relieve some of that pressure between the two surfaces. If I lifted up on that, then it might be easier for it to slide. And so sometimes when an object is set in the surface, it's a little bit hard, and by lifting up, it makes it a little bit easier for it to move left or right. And so when I lessen the normal force, the frictional force also goes down. When I push down on an object and I increase the normal force, that also increases the frictional force. But ultimately, how easy it is to push something over one surface really just depends on the mutual properties of the two surfaces. And so I've defined these two variables, these mu s's and these mu k's. And what mu k and mu s are really determined by are just the type of surface that you're dealing with. And so in order to dive a little bit further into that, I'd like to just give you some examples of what the values of static and kinetic friction are for a couple of different pairs of surfaces. For a particular set of two surfaces, say we have rubber and concrete, wood on brick, or ice on ice, then there's defined values of the coefficient of static and kinetic friction. So if I try to make something that's made of rubber slide across concrete, or a block of ice slide across ice, there are defined values of static and kinetic friction that are present between those pairs of surfaces. So you might wonder, how could I determine what those values are? So I'd like to reiterate that experiment that I was just describing. Let's say I have a block of wood and I'm pulling on it with a force probe. And that force probe reads the force of pulling on that block of wood. We would get the graph that I sketched out previously, where it goes up to a maximum point, drops off, and then it remains at a constant value. And what we could do is we could say, well, if we know that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force, in the event that you're doing this experiment on a flat, level table, then the normal force would just be equal to the weight of the object. So what we could do is we could attach the force probe, we could pull on the block of wood, and this graph would read a particular value here. This value, where that flat segment of the graph occurs, on the vertical axis would be telling us an amount of friction, a force of friction. And we could plug that number in for the force of friction. And we could measure the weight of the block of wood before doing the experiment. And we would know everything in this equation except for the coefficient of kinetic friction. And then we could do an experiment where we varied the normal force by adding weight to the top of the block, or we could get rid of the block and instead use a brick, or instead use a block of ice. And in each case, we should determine a different value of the force of kinetic friction. For example, I would imagine that if we used a block of ice, that the object would start sliding a lot sooner. In fact, the value of static friction and kinetic friction would be a lot less. You could imagine for a much smaller applied force, you would get the object about to slide and sliding. Right? So not only would it require less force in order to get it sliding, which would be indicated by how far to the right this peak occurs, but also it would require less, or not require, but it would have less friction acting on it when it got moving anyway. And so for each set of surfaces, we would get a different value of the coefficient of static and kinetic friction. The kinetic value would be given by the flat segment, and the static value would be given by the peak. And so for these surfaces that I have listed in the table, the values are 1.00, 0.80, 0.6, 0.45, 0.1, 0.03. And there are two things that I'd like to point out in this table. First, I observe that the coefficient of static friction is always greater than the coefficient of kinetic friction. And you can figure that out from the graph too. The value of static friction, that static frictional force will always be bigger than the value of the kinetic friction force, which means then that the coefficient must also be larger because the normal force is the same. But then I also learned for more smooth objects like ice on ice, the values of these coefficients are much less than things that are much harder to move, like rubber on concrete. These values of these coefficients also do not have any dimensions. They do not have any units. And you can prove that to yourself because if you look back to the equation for the frictional force, on the left-hand side the frictional force would be measured in newtons, and the normal force is also a force which would be measured in newtons, which means the one remaining thing in the equation can't have any units. It has to have units of just a number. The last thing I'd like to do is work out an example where we draw a free body diagram that will, I think, really get us thinking about the directions of some different forces, and in particular the frictional force. A while ago, I learned of these little cars that have, I think they're called Mars rovers, and you can stick them to a surface like a whiteboard in a classroom because they have a little magnet on their surface. And they have a little rod on the top that you can wind up, and it's a little toy car. It just drives up the wall. It sticks to the wall because of the magnet, and it drives up because you've wound up the tires. And so by twisting that rod, you give it some speed going up the wall. And let's view this from a different angle so we can better draw the free body diagram. The car looks something like this. The tires are here, and the surface of the car does something like this. And again, like I said, there's like a little rod that sticks out where you can twist that in order to wind up the tires to allow it to move. So in this picture, it's also moving up like this. So if we were asked to draw a free body diagram for this little rover, this little car that drives up the wall, how many forces would we have, and what directions would those forces point? And I would encourage you to stop for a second to try and figure out the free body diagram before I've done it for you. We know that this toy car has weight. There should be a force vector pointing down that's labeled mg. We know that in the body of this car there's a magnet, and that magnet is allowing it to stick to the whiteboard or the surface, and so there should be a force to the right, which is a magnetic force. And oftentimes in physics we use a letter B for magnetic stuff, so I'll just say FB for that magnetic force that's holding it to the board. And if it's in contact with that surface, the wall, then there must be a normal force that points perpendicular to the surface acting on this car as well. And so that will point to the left, and we'll label that N. And then we get to this point, and whenever you're asked to draw this free body diagram, there should be some confusion about what force is making it go up, because at this point the magnetic force cancels with the normal force and I have weight pointing down. So there must be some force that propels the car forward. And so often what happens is somebody will label this free body diagram with an upwards force and have it just labeled F, or F of the engine, or F from the tires, or some imaginary force that might not be the exact force that's acting on the car allowing it to move forward. And so in this case, in order to understand really what that force is, which is kind of mysterious right now, I'd like to zoom in on one of the tires. So I'm going to zoom in even further, and instead of the car, I'm just going to look at one of the tires. And let's suppose that the car is driving up the wall. And if it's driving up the wall, then the tire is doing something like this. Right? In order to go up, the tire would have to rotate clockwise like that, if viewed from the side like this. And if it's moving that way, then let's focus in on the direction of the motion of the tire at different points along the tire. At this point, the tire would be moving up. At this point, the tire would be moving to the right. At this point, the tire would be moving down. And at this point, the tire would be moving to the left. So at each point along the tire, the direction of motion of the tire is in a different direction. And the one that's most important to us today is this one at the contact point between the surface and the tire. And so there are forces that are acting inside of that car. The winding up is me storing some potential energy in a spring or some other mechanism inside that car, which is then causing the tires to rotate. But the force that's being exerted on the car in order to make it drive up the wall is really happening at this contact point between the surface and the tires. Without this force, no matter how much the tires spun, it wouldn't be able to move up the wall. And so let's think about this. At the contact point between the wall and the tire, the relative direction of motion is downward. Right? The tire is trying to move down. And if the tire is trying to move down, there must be a force pointing up on the tire to oppose that motion, right? A frictional force that points up. Because the tire is going to push down on the wall, and so the wall is going to push up on the tire, a frictional force that opposes that motion. And so this force that I'm drawing in red here really is the frictional force. And so there's a frictional force that should be labeled upwards on our diagram. And one great question would be, is that a static frictional force or a kinetic frictional force? And in this particular case, the force that's present there, the type of friction that's present there, is a static frictional force. So we could label this Fs in our free body diagram if we wanted to. And the reason why I know it's a static frictional force, despite the fact that the car is moving, is because at this contact point between the wall and the tire, the downwards motion of the tire is going to cancel with the upwards motion of the tire and the car itself, right? The car and the tires, the axle of those tires and the car itself drive up the wall, but at the contact point between the two surfaces, the relative motion is down. And so those two motions cancel one another, and there's, at all moments in time, there is a static frictional force acting between those two surfaces. And it's this static frictional force that prevents the sliding of one object relative to one another. As long as that static frictional force is present, those tires are allowed to roll like that. And in particular, in physics, we give this a phrase. We say that this is called rolling without slipping. If I'm driving my car around a corner or just driving on the road in general, I would really like it for there to be a static frictional force there between the tires and the road, because I don't want my tires to slip. I don't want to slide down the road. And when the road conditions are particularly bad, this happens, right? When there is sliding that occurs, I lose control of the car. And so the reason why this car is able to drive up without slipping or falling or sliding is because the frictional force present between the tire and the wall is static. And so that wraps up pretty much everything that I wanted to discuss. But to wrap this video up, I'd like to just say a few things. In this video, I think we learned that the frictional force always opposes the relative motion of the object. In most cases, we just think of an object moving to the right, the frictional force points to the left, but here we saw a more complicated example. We also learned that if the object isn't moving and isn't about to move, then the force of friction is simply equal to the applied force. So if I push on an object with a force of 1 Newton and it doesn't move, the force of friction is just 1 Newton. There's no equation necessary. Then we learned that if the object is about to slide, then we can use the coefficient of static friction in the force of friction equation, right? The force of friction is equal to mu times n. And then, lastly, if the object is sliding or moving, then we know that the coefficient of kinetic friction can be used in the force of friction equation.